Before we start, Jeremy, with learning a little bit more about you, I would like to have Eric introduce himself and tell us about what he's doing with the course.
Hi, everybody. My name is Eric Reinflesch. I'm a marketing professor at the University of Illinois. And also, along with Vishal, we began the world's first 3D printing lab in a business school. And we do a variety of educational efforts through our lab. And most recently, we launched just a couple months ago, as our viewers know, the world's first large, massive online course on 3D printing, where I teach the first class and Vishal teaches the second. And this initiative is out of his second class, 3D printing applications. And we have 2 more classes, 3D software and 3D hardware forthcoming, as well as the capstone project class. So stay tuned for more.
So Eric, just a brief, do you have the latest numbers on the course, on your course?
Yeah, latest numbers, we're about 5,200 enrolled learners, and about nearly 450 have finished the class, with more coming. So we're having excellent conversion of learners to completers, which is about double the average for Coursera.
As Eric mentioned, we're doing the second course, and my course has started about 2 weeks back. So we had about 4,000 visitors to that course, and I think about 1,000 active users, and about 10 people who've graduated so far. So they're on a fast track, though. I mean, the course is 4 weeks. So thank you, Eric, for the introduction. Let's move on over to Jeremy. Jeremy, thank you for taking the time. I know you have, about 30 years of experience in the field, so you probably know more than both of us combined in the area of 3D printing and additive. Please give us an overview of, where you are right now. I know, you just changed jobs, and perhaps, your history with this field.
My background is basically as a manufacturing engineer. I used to employ a model maker who told me that I had no soul because I was into production, and production was evil as far as he was concerned, and everything should be custom made, which was fine. So that's my background. I never did convert my model maker into an engineer, and he never did give me a soul. So between the two of us, we kind of worked it out. So my background really was with sort of conventional manufacturing, so CNC machining, a lot of finishing, anodizing, deburring, things like that. And then eventually, while I was doing a university project all way back in the 90s, I came across 3D printing. So I came across stereolithography, which was the first 3D printing process that was commercialized back in 1987. So it's not quite as new as people think. So I came across it then, and started using 3D printing, like sending parts out. And then I bought my first 3D printer in 2004, and my world kind of changed since then. So the previous company I was involved with is Renishaw, who are a manufacturer of industrial 3D printers for metal 3D printing. But way before that, many years before that, as I say, I was working for them, and we built 3D printers, and effectively we were end users. So we were end users of what was already on the market. We started with plastics, we got onto metals, and we learned some lessons very quickly. Some of the lessons were how incredibly useful the technology is when used in the right applications. So the applications that we were looking at the time were for prototyping. We were looking to reduce our product development lead times, things like that. So we learned that it was very good for that. We learned that it also had a lot of shortcomings compared to some of the things that conventional technologies could do in terms of materials and features, and also in terms of production. So when I'm talking about production, we start talking about sort of like producing parts in serious volumes. Now, the problem that I have with 3D printing may be something to do with my background, which is the fact that I come from a conventional manufacturing background. So all the time, when I look at 3D printing, I'm benchmarking it against those conventional processes. So one thing that 3D printing does extremely well is it fills the gaps that conventional manufacturing leaves behind. So for example, if you're going to a part which is ultimately going to be injection molded, first of all, you have to design the product. So that can be done on CAD, and you can run all sorts of simulations. You can do your FEA analysis and all sorts of computational calculations you can do on it. Sooner or later, you need to get to a physical part. And we've had many instances in the past where we would develop prototypes for people, give them to designers who would look at them and go, "Oh, isn't it small? I didn't realize it was so small." And you're like, "How did you not realize that? This is your part. You've been designing this part for the last 3 weeks, and had no idea how small it was." And sometimes people would say, "Oh, I feel silly now because I spent all this time putting these intricate little radii on things, and they're so small it doesn't even matter, and I can't even see it." So it became obvious that there was still a need for physical prototypes in a world where you had these computational 3D models and all sorts of things that CAD does for you, which is a wonderful tool. So it had many, many advantages in that way. And as I say, it fills the gaps that conventional manufacturing leaves behind. So when you get to serious injection molding, that's fine. But how do you develop the processes to begin with? How do you optimize your design? So by its very nature, an optimal design is the best of the alternatives. If you only have one alternative, because that's all your budget and time allow, how can you ever find the optimum? So 3D printing allows you to fail fast, fail cheap. I can't remember whose quote that was. Fail fast, fail cheap. That you can try lots and lots of different design iterations and get to the one that's better. Sometimes you will find that the optimum is a combination between the third thing you tried and the fourth thing that you tried, and that's fine too. Okay. So it's very, very, very good at that sort of thing. One of the things that we had to encourage our designers to do was to future-proof the designs. So when we talk about design for additive manufacturing, that's fine if your product is only ever going to live in the additive manufacturing world. Now, getting straight onto the hype, some people say you don't need to design for additive manufacturing. It's manufacturing for design, not design for manufacturing. That's not true. You do need to design for additive manufacturing because of the limitations, characteristics of the process, and also to make the most of the opportunities that the process offers you. When I talk, sometimes people say, "I don't understand. Are you against additive manufacturing? Are you for it? Because you seem to contradict yourself all the time." I'm neither. So I think that additive manufacturing is great, but I don't think it can do everything that people say it can. And once people stop saying these things, stop making these claims like complexity is free and your limitation is your imagination is your only limitation, then do you know what? It is going to be meeting what people say, and people are going to realize what a fantastic technology it is.
Yeah, I think we've had quite a bit of moderation perhaps in the hype last year, particularly looking at the, how the stocks have done of 3D Systems and Stratasys, sort of the big three. And it seems to be picking up again. Many of the forecasts that, even I have reviewed in the course are now posing a very optimistic picture of the growth. And one of the messages that came out repeatedly is that increasingly we are seeing end-use parts being created more often using additive. To reach that stage with end-use parts coming through additive, what are some challenges that we still need to overcome?
Okay, so some of the challenges of it, and now it's being addressed because there are more systems now. We'll talk about the future going on later. But there are now more to do with automation. And again, this compares with competing with existing technologies. People in the additive manufacturing world have been saying for years, talking about the killer app. Where's the killer app? When the killer app comes, the additive manufacturing will explode because people aren't going to adopt this technology simply because it's cool on an industrial scale. They'll adopt this technology when it offers positives against the alternatives. But there are a few examples where this has happened and it's kind of snuck in under the radar. So an example of this would be hearing aids. Hearing aids were first tried for customized hearing aid, where basically the idea is you put a putty in your ear, you get the patient to yawn a couple of times so you capture the internal geometry of the patient. You then scan that geometry and you 3D print a shell into which go your existing conventional hearing aid electronics. And that hearing aid is then custom made for the patient in terms of comfort and the fact that it can sit inside the ear canal and be a lower visibility. Now, this is a killer app that was first tried in about 1998, and it became widely used in about 2003. Now there are about 1 million a year of these things being produced, and people aren't talking about this because when its wide-scale adoption happened between 2003 2005, nobody was talking about 3D printing, and now people are talking about 3D printing. The 3D printing community is sick to death of talking about hearing aids. So this is an example of something where an adoption has taken place, but nobody's known about it. Now, some of the boundaries for 3D printing are dropping as time goes on. One of the killers for aerospace has been qualification. So people have always said 3D printing is a really good fit for aerospace, and it is, because you can make geometries where you can take weight out of components. And in aerospace terminology, weight equals money. So being able to produce weight is a functional advantage of the component. The big disadvantage in terms of aerospace is qualification of the parts. Now, I'm quite a nervous flyer, so I'm really glad that the controls around aerospace components and what goes into an aircraft are so tight and so stringent. But one of the big problems with 3D printing historically is it's been a closed box process. Okay, so you put your CAD files in, something happens, every now and again you'll see a glow coming out the window, and then your parts come out. So what's happening now is that manufacturers are now having to put data capture onto these systems. So they're monitoring things like laser power, bed temperatures, a lot of the parameters which are going to affect what's happening during the build. And as that goes on, the boundaries to adoption will fall.
Eric, did you have any questions for Jeremy right now?
I think in line with Jeremy's most recent comments about qualification and getting metrics on 3D printed parts. If he knows anything about our friends Zach and Evie, who sorry, not Zach, Zach and Annie,
yeah,
who began Sendball,
yeah,
which is doing these sort of things. So what is the role of these? I think one of the exciting things about 3D printing and additive manufacturing is not always the hardware or materials or the software, but the associated infrastructure.
Yeah.
I think, is there a market, Jeremy, for firms, individuals to get into the certification process, and what other types of ancillary business opportunities exist in this space?
I mean, there's a whole industry that never gets anywhere near a 3D printer.
Yeah.
So, for example, softwares around this. There's a company in Belgium called Materialize. They're based in Leuven, and they are a massive company, and they do several things to do with 3D printing. So, firstly, they offer as a service bureau. Okay, so you can submit files to them, and they will manufacture them for you. They've actually done some of their own hardware development where they've made large-scale SLA systems. They made one called a Mammoth, being stereolithography, so that they can produce parts that nobody else can. They also offer a service where they will manufacture and design fixtures for coordinate measuring machines. So somebody will come along and they'll have a component and they can bring it over to this place, quick fix, and the Materialize will then manufacture that for them. They also develop and sell software. So they're probably the market leaders when it comes to STL file fixing software. So they have a software called Magix, and this becomes sort of like the industry standard. It's not cheap. We're talking sort of £4,000 pounds sterling per seat for this thing, where you can submit your files and it will analyze the files. It will look for failings within the file, check if they're watertight, inverted nominals, all these kind of things which will stop a file from building, and it will fix them. So it will go through, allow you to manipulate and fix the things manually, or it will do it automatically. What they've then done is they've then expanded that software suite. So they would do things like support generation. They will automatically generate supports, and they have their own proprietary support structures that they will put on it. They have another spin-off business called Materialize.mgx, where they have their own retained designers who are experts at designing for additive manufacturing, and they design their own products, which as a customer you are then able to go along and purchase yourself. So you can purchase all these products, and like lampshades and things like this, They purchase a designer, a wonderful designer called Yanni Kittonen, who used to work for a company called Freedom of Creation. He's an expert in designing wonderful designs and really sort of like grabbing hold of the sort of opportunities that additive manufacturing give you, so people are able to purchase that. In the medical field, they have software that will allow you to take CAT scans. So it will take individual slices of CT scans, and you can then convert those into 3D files. So people are now using them to produce things for surgical fields. So they're using them to 3D print bones and skulls and things like this, which surgeons can then take into the theatre and plan operations with. Also things like implants, so titanium implants for replacement of bone parts and spinal implants and things like this. So Materialise do all these wonderful things, and they've grown to be a big company, and many people in the industry know them, but they don't manufacture or sell a single 3D printer. That's not what they do. It's all about the fields and services which are around them. Shapeways is another one. They're a spin-off of Philips, and this is a company, and they've become the biggest service provider in the world now, where they basically act as a hub for people to send in files. They started off on 1 or 2 platforms. They've now expanded their material offerings and the number of platforms they do. There's also an innovative company called 3D Hubs. And what 3D Hubs have done is they've looked very cleverly at people who operate existing 3D printing services, whether they do it commercially or whether they do it in-house. And what they basically do is they sell the spare capacity that these people have. So you can submit a job to 3D Hubs. They will look along their network of providers, find a space where there's capacity in the people's production plans, and fit your part in. So it's a service bureau without even a service bureau platform. So there's lots of people who don't actually manufacture 3D printers or 3D printer materials.
We have actually Shapeways and 3D Hubs are both partners in this specialization. So we've talked about their role in the ecosystem, and they're also helping with providing some discounted printing for our learners, because part of the specialization, once the learners do the software and the hardware part, they will actually participate in the capstone, where they will go from a prompt that that is focused around their needs, and then go from that, use the design thinking approach and come to a potential prototype. And to help them with those prototypes, these partners will provide discounted services as well. So I know 3D Hubs has done great in terms of providing access to our learners, across the world as well. Jeremy, you've said a few times the concept of design for additive. Now, to the beginner learner who's probably going to take the 3rd course in the series and learn software, and we are giving them the basic software as Tinkercad and then Fusion 360. They're also learning some basic sketching to start with 2D and then go to 3D, and then they will learn some skills in scanning as well. So if you can give some direction on the people who just learn CAD and who are starting out, what is design for additive and how is it different from just learning CAD?
Okay, the first thing you need to do is to understand the characteristics of additive before you can truly design for it. So one of the key differences between designing for a subtractive method such as machining is, in subtractive method you would start with your raw material, your billet form, which would normally be prismatic, and if you're designing for it correctly, you would minimize the amount of material that's taken away. Now, of course, conventional CAD systems are very good at that, because this is how they're built. But in the case of additive, the key difference is put material where you need it, as opposed to subtracting from existing material block. Okay, so that's one key thing. So an approach for that may be, if you're looking to design something like a pen holder, for example, handy little tip. Rather than starting with a block and putting a hole through it, start with the pen and then see what material needs to go around that pen, okay, to restrain it. And then what am I going to restrain that to? I'm going to restrain it to the desk, okay, so I'm going to add material there. So there's a fundamental difference. One of the other key characteristics that you need to understand with 3D printing is about supports. Now, the supports can make or break a 3D printing system. So in the case of FDM and stereolithography, which most of the home and hobbyist and desktop 3D printers are, you have a physical support system. In those cases, it's a scaffold support. So you're looking to minimize the amount of scaffold support that's on there. You also need to think about your support removal. So for example, if you're building a sphere and you want a hollow sphere, how is the support from the inside of that sphere going to come out? Whether it be a powder or a scaffold or whatever. Can you have drain holes on there? Does it have to be a complete sphere? Can it be a lattice structure? Lattices are another great way of lightweighting design. So when you do with conventional design, you don't need to worry about the internal solid block. And in some cases, of course, that's a good thing because it provides thermal pass, and it means less machining and lower manufacturing costs. With 3D printing, you can think about taking that volume of material out where it's not required, but you have to consider how the support is going to be removed. So really, the top tip would be understand the characteristics of your process before you design for it.
Let's go ahead and take a question from the audience. So we have S. Nagarajan, who's an electrical engineer from India. He's interested in mind control bionics. So I guess he's looking at the interface of sensors and then creating prosthetics or I guess enhancements if possible. So what are the what are some insights in that area on interfacing? We do talk about, even in some of the courses that we run in our lab, we're increasingly seeing people create smart objects and, embedding computation. And since you can make the structure in complex shapes and you can conform to the human body or, put it on wearables. So that is an interesting growth area. And we do talk about a bionic hand made by, a student in Japan, who's made it open source, the EXII project. So I guess any insights on where to get started in that area and what's happening in that area?
Well, I mean, there's several things happening in that area. I mean, but still, by far the biggest area is to put electronic tracks onto the outside of components. So you have things like aerosol jet, for example, where you can put conductive materials down onto the surfaces of existing 3D objects. But that now what you're also having is what's claimed to be 3D printers, a lot of what's claimed to be 3D printers in terms of electronics, where they're actually using conductive nanoparticles. So things like silver, for example, is a highly conductive material. You can get away with good conductive properties over low volumes being deposited. But a lot of that is still, in essence, two-dimensional. One of the problems with putting circuits onto three-dimensional objects is the population of those circuits, by which I mean in conventional electronic lines, you have what's called pick and place. So you start off with a PCB, that's a two-dimensional object. It would go through a pick and place machine where basically a robot would take the electronic components off of reels or trays or cassettes and put them on with the addition of solder paste onto the pads that are sitting on the tracks. Where electronics is going now is the conductive path actually being a part of the 3D structure. So we're now talking about conductive materials being built inside the object as it's being created. So as opposed to stopping an object, putting a sensor or whatever in, and then continuing to build over the top, which is not a good automated process, but can be done. We're now talking about making conductive tracks through the object. So one big claim that's coming with this is Hewlett-Packard with their multi-jet fusion machines. So what they're saying is that it's a spray binder process. So you're actually adding to an inert powder, you're adding a spray binder on. Now the binder is changing the characteristics of the powder as you build it into a solid. And what they're saying is that by putting on conductive binders, you're able to create conductive portions of the part that you're creating. Now, at the moment, the Hewlett-Packard system, they're taking pre-orders and they're looking to ship in October on the small machine, and the bigger machine is going to be released next year. and at the moment it's just a single color machine. But they have a whole range of materials which right now are in qualification over in Spain. That qualification process doesn't end until August. So after August, you're going to hear a lot more from Hewlett Packard about being able to produce conductive parts.
Well, thank you. Hopefully, Nagarajan, that's given you some insights on that. We have another question from Ray Fraley, and I think he's referring to more in terms of using desktop printing applications and the use of multiple materials for support, and figuring out what's the right material for supports that we should be looking at, and I think it's at the desktop level. Ray, you can correct
Yep.
me if I'm wrong. So Jeremy, perhaps you can comment on multiple materials at the desktop level. What are the things to watch out there? Okay,
so desktop 3D printers, obviously a lot of development on that. It started off as just FDM or FFF as it was called, fine filament fusion, because of the RepRap project from Bath University. However, you now have desktop SLA printers as well, because of course of Formlabs and their form machines. And people are now talking about desktop SLS systems. So as the patents run out, the entry barriers are going lower. Now, with the 3D systems, they have a range of cube machines, which is their desktop offerings. Now, one of them last year started offering a water-soluble support, which is quite a breakthrough in terms of at-home 3D printers. Water-soluble supports are much quicker and much better. Now, two of the drawbacks with non-soluble supports, so supports that have to be removed, is you need physical access to get in there and remove the supports, okay, which can be impossible depending on the geometry of your part. And secondly, because of the support witnesses that it leaves. So when you remove supports from a part, you're left with pips or stubble or whatever, depending on the support structure that you're trying to use, which then have to be sanded off. Now, you've got two drawbacks there. Firstly, again, you need access to sand them off. Secondly, you have the time that it takes, and also the degradation of accuracy, because if your 3D printing system is claiming to print parts between plus or minus 50 microns, your 50 microns has disappeared by the time you've got there with sandpaper to remove the support witnesses. The best thing to do is to design so that you don't use support, but if you do, it hurts me to say this, but the 3D systems water-soluble support is a good tip.
Maybe add on to the comments about the supports as well. I think I agree with his last comment. If we can avoid altogether.
Yeah.
So I think and we haven't talked about this yet in the specialization. This I think will be in the hardware course taught by Ultimaker. But in addition to having the slicing software create the supports, there could be strategic supports placed in the actual design program itself, right?
Yeah.
In the model. So there's two ways to do that. And I wouldn't be surprised that Jeremy mentioned 3D systems, which actually I think has pulled out recently of the desktop market. All the machines could probably still be found at Amazon, other places.
Yeah.
I wouldn't be surprised to see other 3D printing manufacturers come out with similar, soluble supports and dual head printing. I know MakerBot had been playing with that as well in earlier versions of their replicator machines. That would be, and we know that materials are advancing very quickly, perhaps more quickly than the hardware in this desktop market. And so I think this is hopefully a temporary problem that will be solved through technology in the coming years. But a question for Jeremy, one thing I'm always interested about, we have gurus like Jeremy, is the future predictions. I draw an analogy of 3D printing today in 2016 being where desktop computers were like around 1982 or 83. And we see how quickly that has changed and how different computers are today than they were back then. So Jeremy, what are your thoughts 5 years from now? What will the desktop 3D printing industry look like? Will it be substantially different than what we have today? Or are we talking about sort of minor incremental improvements?
There'll be many differences. Just to break the pattern here and go back to the supports, one thing I maybe could have added is that there are soluble supports on some of the more industrial systems. So with the industrial fused deposition modeling, there have been soluble supports around for a long time before 3D systems introduced theirs. And also there's now water soluble supports for polyjet printing as well. So I should probably mention that as these technologies tend to happen, that those soluble supports will probably trickle down. In terms of what's on the horizon, you've basically got the near field, which are things that have been announced recently within the last 12 months that are coming up, and things in the further future. Now, as far as sort of like the home and the desktop is concerned, what we found historically is that technologies are finding their way to the desktop as the patents are expiring. So the patents expired on fused deposition modeling, and out came the rep wrap. The rep wrap is an interesting one actually, because it's kind of a moonshot project in that it failed in its objectives. The objective was to produce a 3D printer which would replicate itself. They never actually achieved that, but what they did do is to lower the cost. And we also saw Form Labs, a couple of guys out of MIT again, because most of this stuff seems to come from, who brought SLA down onto the desktop. What you're going to find in the future is a lot of these other patents are running out now. So I mentioned SLS earlier, selective laser sintering. Now, one of the big drawbacks with systems such as that are the high build prices. So in the case of selective laser sintering, you're talking about a laser. Now we know that lasers are getting cheaper and cheaper, and you can get away with lower and lower powder. But you're also starting to talk about inert chambers, and you're talking about sealed chambers with inert gases flowing through them, longer cool down cycles, things like this. So I think what you're going to have to find is going to be two things. Firstly, patents expiring, which they are all the time. And secondly, economies of scale. So as more and more of these systems come out, they will become lower and lower cost. Now, I mentioned polyjet printing to you earlier. So this is a technology that's been around for a long time and was based on inkjet printing. So it started off in inkjet printing over in Israel, and they realized that as well as printing in 2 dimensions, they could add the Z-axis or the Z-axis, and then start printing in 3 dimensions instead. That is a very scalable technology, and I can see that lending itself very well to home markets, especially as the material prices are gradually coming further and further down. And what you're finding now is that some of the bigger chemical companies, so people like DSM, BASF, people like this, and 3M, are now getting more interested in 3D printing, and the material costs are going to crash. So it's not just about the patents running out, it's things like that. So I can see that polyjet will be entering the home market before things like selective laser sintering. Now, we've also found from universities metal systems. So there's a lot of interest in metals. And I had a guy say to me a little while ago that you could now buy a metal 3D printer for less than 500 quid. And I had to tell him he was wrong, and I had to tell him he was right at the same time. The reason I say that is that you can now print low bismuth alloys and solder and things like this through what is essentially FDM platforms. So 3D printing, as we think of it on an industrial scale, with the laser systems, etc., is still too high cost for the high scale market or for the home market. But as far as the home market is concerned, where there will be compromises made, things like metal 3D printing will be coming into the home in the next 5 years. Polyjet will be coming in the home in the next 5 years, and possibly selective laser sintering, but in a different form than it is now. And it may well be that it's a lower performance version than what you get industrial.
Well, thank you, Jeremy. We had another question about food 3D printing, and in fact, we have another speaker tomorrow, Dr. Charles Mire, who's going to talk about soft materials and 3D printing. But if you had some quick thoughts on printing food, that'll be nice.
Sure. One of the things with 3D printing of food, again, it goes back to this hype thing. People have spoken about 3D printing of food as, you know, it's going to save us all on world food shortages and etc. One thing that is absolutely critical to remember about 3D printing of food is you are reprocessing existing food. Okay, you're not making burgers out of thin air here. You're making burgers out of the constituent parts of burgers which are being printed down. I think as far as 3D printing food is concerned, are we going to make any new culinary masterpieces? No, we're not. Where it's going to lend itself very well is where people come in and they want their customized versions of food, for example. You could also use it to produce things where you deliberately want to take ingredients out. So, for example, someone with a gluten-free diet or somebody with food allergies and stuff like that, it will allow them to produce food. 3D printing, remember, at its core, at its base, is all about producing geometries layer by layer by layer, not about some magical chemical process. But no doubt, as I say, you'll hear more about that tomorrow.
You know, we never really heard about how, you know, you moved into the new firm, which is Sartorius Stedium, if I said the name right.
Sure.
So how are you using additive? You know, I know Renishaw, you know, you spent 28 years there. So what are you working on at this, you know, at the new job? You're the director of additive there. So tell us a little bit about how you're using additive at your firm.
Well, at the moment, Sartorius doesn't use additive much. Sartorius, without wishing to give anything that's going to be too boring and not wishing to do an advertisement, Sartorius is in essence a biotech company. Okay, so they make lab equipment and they also make bioprocessing equipment. So when we talk about bioprocessing equipment, we're talking about filtration, separation, fermentation. So it's the sort of equipment which pharmaceutical industries would use for producing vaccines and medicines. It would also be used for sort of like medical sample analysis, so separating out DNA, proteins, antibodies, things like that. Now, there's a couple of sort of like core things which we're looking at doing at Sartorius. One of them is to leverage additive manufacturing for the same sort of ideas that we were doing at Renishaw, i.e. reducing design times to market. So you're looking at producing physical prototypes, design concepts, and all the kind of things we were talking about before. Some of them can be used, of course, just for marketing. Some of them can be used for more functional testing. But one of the most interesting challenges at Sartorius, which I never had at Renishaw, is the chemical properties of the materials. So when we talk about material properties, we may talk about their physical characteristics. Are they transparent, translucent? Are they opaque? We may talk about their mechanical properties. So you start talking about your Young's modulus and all those kind of interesting things that we all learned about engineering bending theory and then forgot 5 minutes later. So all the sort of things you talk about with mechanical properties, but also biological properties now. Okay, so there's a lot of talk in the 3D printing world about biocompatible materials, and this gets people very excited because they see things like titanium and cobalt chromium implants going into patients, and they think, oh great, you know, 3D printing is, you know, we can now make new body parts. We may have seen the TED talk of Dr. Anthony Atala talking about his 3D printed kidney and bladders, etc. But biocompatibility can mean lots of different things. It's almost like using the term strong. Well, what does that mean? So one of the things for us in terms of biocompatibility is we don't want something that is antibacterial, okay? So if you want to use something in an operating theatre, or you want a drill guide for dental, for example, that's an application that's been around a long time, antibacterial is great because you don't want any germs to lie there, you want to get it in the patient. Another useful characteristic in 3D printing is materials being inert. So I mentioned selective laser sintering earlier. So nylon 12 is a base material that's been used in selective laser sintering for a long time. And that came really from sort of like the motor industry, nylon 12, because it is an incredibly inert material. It's good for fuel lines and things like this. But if we put a material into a bioreactor, which kills the cells that are in that bioreactor, we're in big trouble. Because that bioreactor may be a 2,000 litre container, and inside there, the fluid may be 10 or 11 million euros worth of cells that are sitting in that fluid. And if you have a material there We have to carefully control the extractables and the leachables. What we don't want is any agents that are going to come out of that material and interfere with the cells in any way whatsoever, either releasing bad cells in there, mutating the cells that are there, or killing the cells. So it's a different sort of challenge that we're facing at Sartorius than we faced at Renishaw. Some materials already exist that claim biocompatibility, but you have to look at the stability of the matrix. Are chemicals going to leach out once you get above 40 degrees, 50 degrees? What's going to happen there? Are they going to break down over time? So there are some different challenges, but at the same time, we still want to make our jigs, our tools, our fixtures. We still want to know what these things are going to look like. So yeah, it's an interesting challenge.
I think we had interviewed another researcher in the bioprinting area, and she was talking about a related challenge, not in the material of the tools and fixtures, but the biogels itself. That is a big challenge, is making sure that that medium can support the cells and the growth. So I guess one is the challenge in the biogel itself, and then there is the related chemicals from the tools and fixture that you're using for the testing. I mean, in fact, we have quite a few students come into the Maker Lab. We have about 18 3D printers there, and several of them designed custom test equipment for their experiments. Of course, not all of them are really worried about the chemical leakage into the materials. But that's, we've seen a lot of that happen at the lab as well. So I think I have, we have one question from Jerome Castaneda, who set up his own sort of consulting startup, I think, in 3D printing. So he's looking for career options in using his skills in mechanical design and leverage 3D printing, and some directions on where an individual with design skills, how can they leverage 3D printing to set up a new business. What's the right place to enter in for an individual with design skills and knowledge of 3D printing? Any guidelines on that?
Well, the first thing I would say to Jerome is don't be so desperate to go off and set up your own business with your own killer application. There are a lot of opportunities out there within existing companies, because what you will find is you will have companies which are full of designers that have maybe been there the 20, 30 years, and they all wear the same tweed suit that they do every day. But one of the things we found out very quickly at Renishaw is, by telling a designer that we now have these additive technologies that can turn parts around much quicker and whatever, all they see is, oh, I can get these prototypes made quicker, and they would carry on designing in the conventional way that they always have. And as I mentioned earlier, if you don't sort of make use of the opportunities that 3D printing gives you in terms of geometries and lattice structures and some of the other things that we mentioned, then you're probably designing wrong, and you probably find that additive manufacturing isn't the way for you. So there is an opportunity, and it's a big opportunity now, where companies are going off and spending lots of million. We spent £5 million at Renishaw bringing additive manufacturing in and combining it with our current processes, where you need to come in with the different design approach. And someone with the sort of skills that Jerome was talking about may well find that companies such as GE, which are making huge investments over in the States and in Italy and in India and all across the world, are looking for designers just like him. So he doesn't necessarily have to run out and make the next ski clips.
As Jeremy was talking about all these new developments, one that sticks in my mind, and we haven't seen it yet, but it's forthcoming later this year, is Mattel, the toy company, which is coming out with a children's toy 3D printer. I guess sometime in October is the planned release. And to me, that's exciting, and it's only $299 US, because I really think that, as I think Jeremy's talking about, old habits are hard to change. And once you reach a certain age, it's hard for an old dog to learn new tricks. So really, I think one of the advances in this technology will be the next generation. And so once we have children who are using these as toys or in the classroom, they're going to demand that at colleges and universities. and then they'll have the skill set and also demand it in the workplace. And so it seems that we're perhaps a generation away from the full potential of this technology. I just wonder what Jeremy thought about children getting involved, even with something as simple as a toy printer.
I was told once that it's a sign of how old you are by how amazed you are how young people deal with technology. So the more amazed you are that the fact that kids can pick up a tablet and a smartphone and whatever, it's a sign that you're getting on. I think the thing to answer your question there, Alec, is these people, they're going to look at this technology and they're going to challenge it in ways that we've never challenged it. Because of the problem with people who are sort of like the wrong side of 30, such as myself, is we're looking at this and we're going, oh, wow, this is new, this is great, what can I do with it? What are the opportunities? Whereas when the sort of children you're talking about that are sort of dealing with the Mattels and the Dremels and the low-cost things, by the time that they reach graduation, they're already going to be bored of this. They're then got the hunger and the appetite to push the technology on and say, okay, this is conventional. What can I do that's beyond the conventional? Right now, for people in my generation, 3D printing on a desktop is beyond the conventional. The sort of career that people like Jerome are going to have, it's all very exciting. And I think that's the thing, that's the key for them, is the fact that because it's so everyday to them, they're going to look at it and say, right, what can we do next? Let's not worry about the advancements that have happened over the last 30 years. That's done, forget it. 30 years ago to someone who's 3 years old may as well be 200 years ago, 500 years ago. It's as revolutionary as the birth of the steam engine or fire, because to them, it's been there since year zero. And what we're going to see is much more innovation coming on in the future by people who are bored. Now, the reason that I say that is that people that are bored are much less likely to stick with the status quo, okay? Because they're going to look at the status quo as it is at the moment and they're going to go, that's the current situation. What can we change? What can we do differently? How can we build on this? As opposed to looking at it and going, this has already changed things. So for them, it's not going to be about searching for the killer app, as people such as myself has had to do. It's going to be turning the technology on its head.
I agree.
I think, Jeremy, that's a great message to end on, and we're trying to convey that through the course as well. That with the democratization of these tools to, as we say, turn ideas to objects, the sort of the current generation or the next generation will do things that we can't even imagine, because we are still comparing what we have today to what we had, as you say, 30 years ago. So their concept of what's possible will be with reference to what's available today rather than what was available 30 years back.